I'm going to get back into the advanced areas, and really this is because this topic is only tested at the A levels. There is no testing of this topic at AS or any of the earlier levels, so I figured I'd put it here. And that is the oblique collision of two spheres, right? So I have that. I briefly touched upon that. I've talked about collisions and in elastic collisions in the core playlist, but here it's purely spherical objects colliding. So we're just going to discuss a few important things to remember and how these problems are addressed. And I think conceptually, I want you to just, I've obviously drawn two spheres here, a section R1, mass 1, radius 1, approach velocity U1, written as a vector A1i plus B1j. I'll go to it because they might give you velocity. They might sometimes state it as a vector. Similarly, you've got sphere 2 with mass 2, radius 2, velocity, approach velocity or initial velocity U2 could be addressed. In some problems it's addressed. And then you've got the velocity stated as a vector in some cases. But I want you to remember the most important thing. I briefly touched on this in the core playlist. And this line here, right? And I'm gonna just call this line AB just for the sake of it. This is very, very important. This is the line of centers, right? So just keep that in mind. Line of centers, line of centers. And your problem can often give you, specify a directional vector for the line of centers. It can actually tell you that, oh, the line of centers is along J, or the line of centers is inclined at 30 degrees to J, right? Which kind of gives you an idea where the line of centers is. And then specify the force vectors that, or the force and the angle between them and the line of centers. But anyway, let's get to the line of centers. What's important to remember here, right? You remember three things when it comes to line of centers. One, the impulse momentum principle. I is equal to delta mv. This is applicable along the line of centers. Remember why? Because we talked about resolving forces. These are oblique collisions. So there is a resolution along the line, and there is one that is along sort of the horizontal. So remember that too, right? What else happens, right? Restitution is applicable along the line of centers. So the change in separation velocity divided by change in, or the speed of separation by speed of approach. What else is applicable? Total sum of momentum is constant. Conservation of momentum is applicable. These are along the line of centers. Very important. Don't forget these, right? If you know these three, you can pretty much solve all of the problems, because everything else is just geometry, right? Everything else is just geometry. So here's, we'll start with this first. Something to remember is, I'll extend this. This happens to be one of those cases. It was not intentional. I just picked case, so it may or may not be that this looks this way. But remember here, the geometry of the line of centers, right, is typically, almost always, the line of centers AB so you can close your eyes and know that this is always true. Anytime you have a collision, remember that, right? The other thing you want to remember is the concept of parallel to the line of centers. So these are all parallel to the line of centers, meaning they're all happening along the line of centers. You want to know the perpendicular to the line of centers. What happens perpendicular to the line of centers? Perpendicular to the line of centers is effectively, and I've kind of extended it here, if this is that perpendicular line and a force is now visualized like this, then you know the normal collision is along the line of centers, and then you see the deflection happening here. But this line is important because this defines the angle of approach and the angle by which you get deflected. All of that gets defined here. So this line is good to visualize this, and it's often good to represent these in a XY plane if you want to draw a visual, right? So this is important. What happens along here? The horizontal component, or the component along the perpendicular. So we talked about line of centers, and then one more area is velocity, and I call it cosine theta, right, does not change. So velocity components along that's why it's theta is equal to constant velocity. They do not change, where theta is the angle of incidence. So theta is the angle at which is the angle to the perpendicular. So mathematics, just kind of writing it easily for you. So theta is the angle with the perpendicular. So the approach angle of the of u1, right? What does it make to the perpendicular to the line of centers? That's what we want. That's what we're interested in. Do not forget this. So that velocity is unchanged. So whatever happens along this line, the velocities don't change. Very, very nice formulas. And think about it this way. We learned this as well. We saw this collision where you had the velocity of something coming in, and then you had restitution coming into effect. But we normalized the cosine components here, right? So that's pretty much the same thing that I'm doing here. So important concepts. You remember this, you pretty much solve every other problem here. So I think that's the most important piece here. Let's just try to put some math around it, see what happens if you end up with a problem like this. How are you going to visualize it? So I made it simple for you. I took the line. So I'm going to make these, this is the dotted line. And then the line of centers itself would be that line, right? That's AB. And then you basically bring your velocity down here, right? Whether you're given this as a vector or whether you're given an angle. If you're given an angle of approach, that angle basically is the angle of this line of centers with the horizontal. That might be called a line of the angle of approach, right? So that's the angle with which one sphere approaches the other sphere, but that doesn't necessarily mean that's the velocity vector. So something to remember. Sometimes you're given a velocity vector and this one's stationary. You've got to now figure out how you're going to set up the line of centers, right? You may not have line of centers here, so you've got to play with the geometry a fair bit. But the important relationships to remember is if you write the equation for impulse, you should be able to say impulse is equal to, in some form, impulse is one object to the other. So impulse that A receives, the impulse that A or object one receives will be equal to its change of momentum. So for example, for object one, that will be mass one and its final velocity v1. We don't know, write it as a vector, minus and likewise you'd write for object two, this is one, write it as green, right? Likewise for object two, you'd have a similar equation, which is impulse for object two is mass 2 v2 minus mass 1. They typically like to have a vector involved because in these kind of cases, you do need to have a vector to get an idea of the direction. These equations, not, the directions of the velocity components, you got to be very careful with. So that's a very easy one. And you also have, that's the impulse momentum equation. You also have, you might be given an energy relationship, which is basically the energy lost at the impact. So you have to do that energy loss calculation. We saw the final velocity subtracted by, you subtract the initial velocity. So energy loss does happen, loss of kinetic energy. Again, I can write that relationship. It's the delta kinetic energy right? Which is what happens to the wastage of kinetic energy. It's half m v 1 squared minus u 1 squared. So you might be given this relationship. This is how much energy is lost from this side. You might be asked to calculate also for the other one. You can write an exactly identical equation for the second object, and you can get total energy that is lost as a sum of those two. So delta K1, delta K2. So you can, and then you have delta K is equal to, so you can write E2 similarly for E2, and I'm not going to write the whole thing. These two add up to give you the delta K, which is the lost K kinetic energy. So that's another relationship, important to remember, right? Restitution, you are fairly familiar, but you need to get the angles correct for restitution. If you have U1 approaching this way, and I know this is my U1, I need to have this angle established correctly. In this case, I have my U1 coming in. If the vector is transported here, I could tell you that, sorry, if it's 30 degrees, if it's coming in 30 degrees, if this is given as 30 degrees, then I'll have to figure out, based on the length of these, I'll draw the geometry, and I'd be able to say, okay, maybe the approach angle to the horizontal here is 60 degrees, and maybe here, if this is the horizontal, or maybe that's another 60 degrees. So I've done the math here, so you have to remember this very, very carefully. You have to calculate this angle, right? And you have to calculate this angle. These are the angles that are valuable, right? I'm not gonna, and that's the line, the perpendicular line, which you need to map here, and this is the angle you need to get. So remember that, very, very useful. If this angle is theta 2, and if this angle is theta 1, then your restitution equations will be written as, maybe I'll put it here, E would be equal to, and you can write the same thing, and there it will be equal because restitution is given for two objects. So whatever you see is, you'll have to get the separation components. So it is not, it will be the component of this along the horizontal. So and the component of U2 along this horizontal, right? So the sine theta and the sine, so the two different sine values. So this will give you the speed, and you could do this as U1 sine theta 1 minus or add, depending on the direction. So this is where you have to be very careful. U2, now separation, so this is still approach, so you're still on that, your vector is very clear, sine theta 2, and then my apologies, this would be not theta, I made a mistake, that's the denominator, U1 sine theta 1, right? That's approach angles theta 1, and this would be theta 2. So these are both related to approach. They would be here. Again, you have to figure out, whether it's a positive or negative. Most cases they are positive, and then you would write U2 sine theta 2, and then on the numerator you would have the final velocities, that is V1. Again, you'd be resolving them horizontally, so they won't be theta. It will be another angle here. Let's say it's alpha 1, and here you'd have an alpha 2. So then there would be alpha 1 and V2. So this would be V2, and this would be alpha 2. Right? Remember that. I'm keeping it very generic. Your real problems may give you some angles, but this is the mental idea. So that completes it. And finally, you have your momentum equation. Hopefully, I don't make any mistakes here. But remember, it's basically the mass 1, U1, change of momentum is along the line of center, so it will be sine. So likewise here, remember the sine and cosine apply because the impulse changes along the direction. So I have to capture that angle as well. So u1 sine of theta 1, right? That's the momentum of the first sphere plus m2 u2 sine of theta 2 is equal to the final state, which is again m1 v1 sine of alpha 1 plus m2 v2 sine of alpha 2. And let me help sort this out as well. So this would be m1 v1 sine alpha 1 minus m1 u1 sine theta 1, right? So yeah, so that effectively gives you the relationships that you need to start plugging in. If you're just not to make sure you're not confused, it's sine theta sine alpha 2 minus m1 u1 sine of theta 1. Hopefully that's clear. So remember that if you're given this, if they are vectors, you need to make sure that the vector multiplication is done. You might not have the sine alpha, or they might not give you angles, they just give you vectors, and everything is done as vectors. And be careful to see the direction against which the vector is analyzed, because if they tell you the line of centers is, say, 5j or 3i, then you know that they're pretty straightforward. Most problems have fairly straightforward. They don't complicate the math, but it's the relationship of, even if you wrote it as a vector or whether you wrote it in as a component, you can't forget the angles that you need. If you have the impulse, restitution, energy, and conservation of momentum relationship sorted, you are in good shape to handle this. So I'll leave you with that. Try some practice problems. I think it's pretty fun, but they add the geometry portion, which actually makes it quite interesting as well. Right? Good luck with it.